Assalamualaikum warahmatullahi wabarakatuh and good day everybody. Let's continue our lecture for week 3. We're still in the same topic, pressure and fluid statics. Okay, before we have learned the Pascal principle P equal to F over A, and for this week we're still in the same concept of Pascal principle, but we extend the equation to the pressure problem inside the liquid. Let's recap what we have learned before. I think most of you have experienced doing this experiment where a container full of water and there is several holes at the side of the container. During the experiment, we found that at the highest hole, the jets are weakest, while at the lowest hole, the jets are strongest. As jets are linearly proportional to the pressure, we found that the pressure will increase with depth. So actually the equation for pressure inside the fluid is still using the Pascal principle. Okay, let's start derive the equation. We know that P equal to F over A, or P equal to wedge per unit area. And then we know that wedge are equal to M times G. Okay, now we got the equation become P equal to mg over A. We also know that M equal to density times volume. Now the equation become P equal to rho Vg over A. For volume for cylinder is equal to A hash area times the higher h of the cylinder. So we got that P equal to rho A hash G over A. We can cancel the A, and now the equation become P equal to rho hash G, or normally we say that P equal to rho G hash. Okay, you can decide how you can remember this equation. Rho G hash, hash rho G, rho hash G, or anything. It is still the same equation for the pressure inside the liquid. There are several concepts you need to remember on solving the problem of pressure inside the liquid. First, pressure in a liquid at rest increase linearly with distance from the free surface, with the equation of P equal to rho G hash. Okay, the second concept. In case of room filled with gas, the variation of pressure will be too small. Then the variation of pressure can be negligible. Okay, the third concept is the same pressure at all points on a horizontal plane in a regardless of the geometry will be the same as long as the points are interconnected by the same fluid and located at the same h. For a case where the container shape are different, as it is with the same density of fluid and the same h from the free surface, the pressure will be the same. Okay, let's start with some example. Okay, the easiest one. What will the gauge pressure and absolute pressure of water at a depth of 12 meter below the surface? Take density of water is 1000 kg per meter cube, and the pressure, atmospheric pressure, is 101 kilonewton per meter square. Okay, to calculate the P gauge, we know that the equation is rho G hash. The rho is 1000, G is 9.81, and hash is 12. So we get the gauge pressure is 117.7 kilonewton per meter square, or kilopascal. To calculate absolute pressure at this point, you have learned before, P absolute is equal to P gauge plus P atmospheric. So we have gone before, the P gauge is 117.7 and it is given in the equation that P atmospheric is 101 kilonewton per meter square. Just add the P gauge and the P atmospheric, 117.7 at 101, then you got the P absolute is 218.7 kilopascal. Before continue, let's recap some information about density and specific gravity. Okay, for density is scalar quantity and defined as the ratio of mass per unit volume, or normally we use as the sign of rho for density, and rho equal to m over v. Okay, for specific gravity also known as relative density, or it is the ratio of density of a substance to water. For the equation is Sg for the specific gravity is equal to substance density rho over density of water, and we know that the density of water is 1000 kilogram per meter cube. Okay, let's do some example on density and specific gravity. Okay, the first example, calculate density and specific gravity of a liquid if 0.15 meter cube of that liquid has a mass of 270 kilogram. So we know that density rho equal to m over v, mass is 270 and the volume is 0.15. 270 over 0.15 equal to 1800 kilogram per meter cube. And then to calculate the specific gravity is equal to the rho over 1000. Rho is 1800 over 1000 equal to 1.8. Okay, for second example, determine the density of a fluid that has a specific gravity of 13.6. So you know that specific gravity is equal to density over 1000, then the density will be specific gravity times 1000. So we got here the density of the fluid is 13,600 kilogram per meter cube. Let's go to the second example. Okay, for this example, a tank of oil with one side open to the atmosphere and the other side sealed with the air above the oil. The oil has a specific gravity of 0.9. Calculate the gauge pressure at point A, B, C, D, E, and F, and the air pressure in the right side of the tank. Okay, let's start with point A. Point A is located at the surface of the oil, and it is exposed to the atmospheric pressure atmosphere. Thus, we know that PA equal to P atmosphere. For this point, for this question, you need to calculate the P gauge. Then P gauge for point A is equal to 0. Okay, let's go to point B. Point B located 3 meter below point A. Then to calculate PB equal and then point B located inside the oil, so you need to use the equation of rho g hash. And then to calculate PB equal to PA as the reference plus rho g hash. Okay, for point B, and then PA equal to 0. The density of oil is they didn't give you the density of oil, but they give you the specific gravity of oil is 0.9. Then you can calculate the density. Density is equal to specific gravity times the density of water of 1000. 0.9 times 1000 equal to 900. Okay, now you get the density of the oil is 900 kilogram per meter cube. Okay, back to the question. PB equal to PA plus rho g hash. The density of oil is 900, gravity is 9.81, and hash is 3 meter. Now you get that pressure at point B is 26.5 kilopascal. Okay, let's go to the point C. Okay, same with point B. But point C located 6 meter below the water surface. Okay, now you can calculate for point C. PC equal to pressure at point A plus rho G hash. Pressure at point A is 0 and rho is 900, G is 9.81 and hash is 6 meter. So now PC equal to 52.697 kilopascal. Okay, you have solved for point A, point B and point C. Okay, let's go to point D, E and F. Okay, for point D is the same of point B. It's located 3 meter below the water surface, below the liquid surface. So either you calculate again for point D, or you can just take the pressure at point B because the location, the H is the same. Okay, so you know that PD equal to PB equal to 26.5 kilopascal. Okay, now move to point E. Point E located at the same level of point A. Okay, although point E is inside the liquid, but the location is absolutely same H with point A. So we can get here as the H is equal to 0, PB equal to 0, or PB equal to point A and equal to 0. Okay, now for point F. Point F located, although it is at the liquid surface, but it is but the location is where the air is in a closed section. So there is a pressure at the point F. Okay, because of because the air is located in the closed region. So we cannot take that PF equal to P atmosphere here. Okay, let's count. Okay, PF equal to PF located 1.5 meter above the liquid, above the oil surface that is exposed to the atmosphere. Then PF equal to PA minus OGH. Okay, you need to remember that if it is if the H going down, then it is in the positive sign. But when the H is going upward, so it is need to be in the negative sign. So now PF equal to PA minus OGH. PA minus 900 times 9.81 times 1.5. Now you got that pressure at point F is negative 13.24 kilopascal.